Okay, so we have the second part of the video, which is for the second question, a Chinese postman problem. Okay. Now, first, maybe I have to tell you some history about Chinese postman problem, especially why do we have to call it Chinese postman problem. Okay. Actually, this problem was originally studied by the Chinese mathematician called Kwame Ko. Okay. So there's a link um, for the Wikipedia. Okay, so actually there's another name for this problem, which is called root inspection problem. So if you don't like Chinese postman problem, you can use that same name, but that name is coined in the honor for this mathematician. You can click it and see what um what he did for this problem. Okay, so that is just a history for it, and maybe I go back here. So we have the Chinese postman problem. Now, what exactly this problem study? Well, actually, the Chinese postman problem, okay, is a type of Eulerianization problem, okay, which is exactly what I told you at the beginning in the previous video. But we try to do the problem for some other graphs. Okay, if you remember the Eulerianization problem we have seen previously, we only have not that many odd vertex. Usually we just have two. Okay, two odd vertex, and then what we want to do? We want to find a way to deprecate the edge so that after the deprecation, we have a graph with no odd vertex. All the vertex become even. Okay, and in fact, the resulting graph will have a Eulerian tour. Okay. Now, but if the problem now becomes this, okay, if we have more of vertexes, then the problem will be much more difficult. Okay, why so difficult? Now let me tell you some reason. Okay, now for example, okay, so here I just mentioned that okay, this problem study the Eulerianization problem. Okay, for graphs which have more than one pair of vertex. Okay, so in general, if you have n different of vertex, then there will be m times n minus 1 divided by 2, that many pairs of vertex. So if you go to my notes, okay, so this is one example. Now that example is in fact a sort of simple type problem. Okay, even though for that so-called simple type problem, we still have 4 odd vertex. You can see. Okay, for example, B, C, F, G. This four vertex is are in fact odd. Okay, the degree actually of this 4 vertex are equal to 3. Okay, so they all have the same degree, which is 3, and in particular is odd. Okay, so we have 4 odd vertex, and in particular, how many pairs of odd vertexes? So a pair means you just group them. In 2. Okay, so you can randomly pick 2 odd vertexes from those 4 odd vertexes, and how many possibilities? In fact, you have 6 possible ways to connect them. Okay, so that means you have 6 pairs of odd vertexes. For example, you can do it like BC, BF, or BG, or CF, CG, or FG. Okay, so altogether there are 6. So after you get all those odd vertexes, or I mean all those pair of odd vertexes, then what do you have to do? Well, that is exactly the reason why it makes the problem complicated or challenging. Okay, because there may be many pair of odd vertexes, and we need to check them case by case, right? And now remember, okay, the number of odd vertexes in a graph must be even. I mean, the number of odd vertex. That means you can have either 0 many odd vertexes, or you have too many odd vertices, or you can have 4 odd vertices, but you can never have 7 or 9 or 11 many odd vertices, because by the handshaking lemma, okay, so the number of odd vertices must be even, okay. That means, okay, if you have 4, okay, 4 odd vertices, then you already have 6 many pair of odd vertices. Now the number will become larger and larger according to this formula. Okay, if you have, let's say, 10 many odd vertices, then you have 10 times 10 minus 1 over 2. That is exactly 90 times 10, right? So that will give you, wow, that will, 10 times 9 over 2, that is 45. 45 pairs of odd vertices. That's a lot. Okay, and not just that, after you get those odd vertices, pair of odd vertices, then you have to solve the shortest path problem for each pair. Okay, because remember, especially for this example, okay, from the notes, this graph is weighted. Okay, so there are weights on those edges. Okay, so when you're finding the shortest path, you have, of course, you have to calculate the corresponding weight. So here you have to solve the shortest path problem for 6 times, because you have 6 pairs. For example, between B and C, then you find the shortest path between C and B and C, and calculate the distance. Okay, because you really have to keep the numbers. Okay, and after that, after all those calculations, you still have to pick, okay, those you needed. Okay, for example, now because you want to Eulerianize the graph, so you have to eliminate all those odd vertices. So you have to deprecate some paths. Okay, and what paths do you have to deprecate here? Because you have 4 odd vertices, so you have to deprecate 2 paths. Okay, by deprecating those paths, then those odd vertices will be gone and you're done. But when you're picking it, you have to also think about the distance. That is the weight. Okay, so you only pick those with the minimum weight. Okay, as minimum as possible, I should say. Okay, as minimal as possible. So here, if you look at this example, you just choose this. This one 3, and the other one is 2, the distance. So by deprecating these 2 corresponding paths, that should give you the optimal Eulerianization with respect to the weight. Okay, but see, the problem not easy. Okay, and especially you have to do a lot of work in order to solve it. Okay, so yeah, so this is exactly the problem we have in the notes. Okay, so let me just repeat. Okay, so first you locate, or you just find all those odd vertices. Okay, so for that particular example. Okay, and then you pair them up. Okay, you pair them up. In here you have 6 pairs of odd vertices, and then for each pair you find the shortest path between the corresponding odd vertices. Okay, and then you write down the distance, you keep it, and then you finally pick the 2 with the shortest distance, or shortest weight, or smallest weight, or whatever. Okay, and then you deprecate those corresponding edges, and then the graph will become even. It will become a graph with only even vertices. Okay, this is what you need. Okay, and here I have to point out something quite important. So you pick the 2 pairs of distinct odd vertices with the shortest path and deprecate the edges. So here distinct is sort of important, because now think about it. Okay, if you deprecate those edges which appear twice, okay, then for example, let me explain it with an example. So for example, for some reason you try to pick B to C, and also you pick the You pick the path B to F. Okay, you pick this two paths. Then you will duplicate the edges linking to B, okay, twice. I mean, not twice. I should say. Now, I mean, first you duplicate. Now, see, if you duplicate BC, then you get one extra edge, right? Then the degree of the vertex become 4. Okay. Then if you duplicate B to A, I mean this path B A E F, you first duplicate B to A, you duplicate that. Then again you add one edge to it. Then now, what is the degree for the vertex B? Now the degree of vertex B becomes 5. Okay, so originally it's odd, I know, because the degree is 3, but after the duplication it becomes 5. So you sort of, you know, you're not making it even. Okay, you just add 2. So that means you cannot pick the path which have some common vertex. So here B is the common vertex, right? Otherwise, you are not changing anything on the degree in terms of even and odd. Okay, so that means you have to pick the path with distinct odd vertexes. Okay, that makes the problem even more difficult because I mean, if you if you're not that careful, if you're a little bit careless, then you just simply pick the two paths with the shortest distance and then duplicate it, but without checking whether there's any common vertex. If that is the case, then you will get it wrong. Okay, so you have to add one more line in checking those pair whether they have common vertex or not. Okay, otherwise you might have trouble. Okay. Anyway, so we finished this. Okay, and then maybe I just go back here a little bit. Okay. So here, if you follow the steps, you should get it without any difficulty. But as I said, the difficult part is the checking and is the location of those pairs of odd vertex, because now you have too many odd vertex. Okay. And of course, there's an exercise. I just put it in the notes, in the final page of the notes. You can try it and see if you understand the method or not. Okay. Now, why I keep choosing those problems with that rectangular shape? Okay, I mean for the graph, because this is one typical type of graph which the people are studying in the Chinese postman problem. Okay, now imagine that those graph is in fact the map of what of a housing estates. Okay, for example, A, B, C, D, they correspond to some housing estates. Okay, so it's like you have a row, not a row, but the street. Okay, and they have a parallel estate built on the streets, and then now you want to go through those housing. Not to go through one, go through the housing, but you want to go through those rows, okay? And then you try to avoid repeating those rows as little as possible, okay? Or just imagine that you're like a postman, okay? You are like a postman. You want to go to those buildings and then to get the letters to the residents there. So that's why you want to avoid walking too many distance, okay, along the streets. So that's why you want to save your energy and want to find the Eulerian path, okay. And in fact, this is one of the reasons why we call it postman problem. Okay, Chinese, now you understand why. Okay, Chinese is because of the Chinese mathematician, but why it's called postman? Because postman is because actually it just came from a real problem. Okay, a real problem like okay, you have a street, okay, with two two sets of buildings, okay, and then you want to go through those buildings to distribute those lattice, okay, the postal lattice. So just like postman. So that's why you have that problem to study, okay, and here we have a similar problem, but it's on a longer street, okay. So you have more edge days, and with a more edge days on the street, okay. But in fact, the method is very similar, okay. Again, you just locate those odd vertexes. Well, now here, if the graph is like a rectangular shape, then the odd vertexes are always within the street, okay, not the end of the street like this, not on the corners. Actually, the corners always give you even, okay. The thing, okay, within those buildings, or I should say the streets, will give you odd vertexes, okay. And in fact, for this type of graph, they all with degree 3, okay. Anyway, so you can try that problem and see if you understand the method. Now let me go back to the slide. Now actually there are some related problems. If you're interested to those problems, you can have a look. In particular, you can go to well, actually you can go to Wikipedia, and there are some other related problem. You can take a look at those problems. Now okay. Now, for example, one type of problem is for the directed graphs, okay. Directed graph, that means the graph has arrows, okay, has some arrows, okay, for the edges, so you can only go in one way but not the other way. Now here we have in the previous example, we don't have any restriction we don't have any restriction on the direction of those edges, okay. You can go from either direction, okay. But some graphs do have directions. For example, those graphs we learned for the DNA problem, okay, they have direction. They are directed graph. So for that problem, you have to take account on the direction as well, okay. So for that problem, that will become more complicated, okay. That means, well, if you say, okay, how can we solve it? Well, you can still apply the same method, but after you locate those odd vertexes and want to find the shortest path, you have to take into account of those directions. So that means for your shortest path, you have to follow the direction as well. So if you miss the direction, then that of course that won't be correct, okay. So that's one thing. And then the other thing is the rural postman problem. So we have to solve the problem with some edges not required, okay. So that means in the graph, okay, we have some edges being restricted. That means you cannot go through those edges, okay, for some reason. But that problem, I would say, is not that difficult as the other one, because, well, it's sort of like you are not using some edges. That means you sort of delete those edges, okay. But of course, for some reason, you're not just delete the edge, okay, but try to avoid it, okay. For example, you can say you block those edges, okay. So if that's the case, then how can we solve it? Well, again, this is exactly the same problem as before, okay. So you use the same method, but when you're finding the shortest path, you avoid those edges, okay. So again, that will make the problem a little bit more complicated, but as I said, it's not that crazy as the other one for the directed graph, at least, because for a directed graph, you have to avoid the direction. I mean, not to avoid, but you have to follow the direction. But here, you just have to avoid some edges, okay. Anyway, so those are some restrictions, but the key method is still the same, okay. You still follow the same method to solve the problem, Okay. So actually that's the end for this chapter. Okay, so only two problems. If you think that okay, you might have some more interesting problem you want me to talk about, or you have some suggestion, you can also tell me, and then maybe I will consider that as some extra topics for this class. Okay, but those two problems are the thing I want to talk about. Okay, marriage problem and Chinese postman problem for this last chapter. Okay, so anyway, so if you have any question, you're welcome to send me emails, let me know. Okay, and then as I said, you can use all those problems for the final project. Okay, you can use those in the finals project when you're writing your own story, telling your own story for the final project. Okay, you can try to think about some scenarios which you can apply those mathematics. Okay, so I hope you all enjoy, and that's the end for this video.